I've been to places that don't exist yet. I've walked on Mars, explored ancient civilizations that vanished millennia ago, and visited planets orbiting distant stars. Welcome to the Maximus Traveler, where the impossible becomes your next destination. This channel takes you on journeys that break every rule of physics and time. We explore both virtual and real-life travel destinations across Earth and the entire universe. From hidden gems in your backyard to the surface of exoplanets billions of miles away. Whether it's through cutting-edge VR technology or actual space tourism, we're pushing the boundaries of what travel means. Some destinations you can visit today, others you can only experience through simulation, and some don't even exist yet but will blow your mind. Ready to expand your definition of travel? Hit subscribe, drop a comment about where you want to go next, and let's explore the infinite together.
G'day mate, let's yarn about something that's both a bit spooky and bloody brilliant. Long before we knew what it was, folks would find these funny looking rocks, heavy for their size, sometimes with a weird greenish yellow tinge. Miners in old Europe called one of these minerals pitchblende because it was black like pitch. But they had no clue what was inside it. Stories would pop up. Tales of stones that held a faint, mysterious glow in the dark. This strange energy, this quiet power sleeping in the stone, sparked a curiosity that would, centuries later, change our world forever. It was a question waiting for an answer. This essay is going to take you on a journey. We'll start way back with those old myths and early discoveries. Our timeline kicks off in the late 1700s. Martin Klaproth, a German chemist, pitchblende ore from the silver mines. He suspected an unknown element hiding inside. In 1789, he isolated what he thought was the pure metal. He named it uranium after Herschel's new planet, Uranus. For a while, nobody really knew what to do with it. Its first big gig was in the arts. Glassmaking, pottery. Craftsmen added uranium oxide to molten glass for vibrant yellow and green. Vaseline glass. Uranium glass, often shown glowing. It would glow an eerie green under ultraviolet light. Ceramic glazes like Fiesta ware used uranium for color. People saw it as just a pigment. They had no idea it was humming with an invisible energy. The game changer came in 1896. Henri Becquerel was studying materials that glow after sunlight. He used a uranium salt and photographic plates wrapped in black paper. One cloudy day in Paris, he put the plates and salt in a drawer, Becquerel's discovery energized the scientific community. Marie Curie, Pierre Curie. They suspected the energy came from the heart of atoms. They tested heaps of pitchblende, measuring radioactivity. The ore was far more radioactive than pure uranium, leading to two new elements, polonium, radium. Their work showed atoms could break down and release immense energy. This was the dawn of the atomic age. We'll look at where this stuff even comes from. And I mean really comes from. Think exploding stars. We'll break down what it is on the smallest possible level, get our heads around its atomic structure, and figure out why some bits of it are so special. Of course, you can't talk about uranium without talking about the good and the bad. On one hand, powers our cities, gives us clean electricity, provides tools that help doctors fight disease. All right, so we know uranium is in the ground, but how did it get there? To answer that, we have to look up, way up, and far back in time. Uranium wasn't born on our planet. It's older than the Earth itself, older than our sun. The elements we're all familiar with, like the oxygen we breathe, or the carbon in our bodies, were cooked up in the fiery bellies of stars through nuclear fusion. But stars, even the biggest ones, can only fuse elements up to iron. To create something as heavy and chunky as uranium, you need an event with an absolutely mind-boggling amount of energy. The leading theory for most of the universe's uranium is a truly epic event, a collision of two neutron stars. Visual emphasis. Artist's impression, two neutron stars spiraling towards each other. A neutron star is what's left behind when a massive star dies in a supernova explosion. It's an incredibly dense ball of matter, a city-sized object with more mass than our sun. Every now and then, two of these stellar corpses can spiral into each other. When they smash together, the explosion is one of the most violent events in the universe. This cataclysm, called a kilonova, unleashes a torrential flood of neutrons. In the chaos, atomic nuclei rapidly gobble up free-flying neutrons. The R process, rapid neutron capture, building the heaviest elements, gold, platinum, and uranium. So this cosmic treasure is now buried in the Earth's crust. But it's not just lying around in big, shiny lumps. Uranium is typically found in very low concentrations, mixed in with other minerals in an ore. To get it, you've got to dig. One is open pit mining, where they dig a massive hole in the ground to get at ore deposits close to the surface. The other is underground mining, where they dig shafts and tunnels deep into the earth. A more modern method, called in situ leaching, involves pumping a solution underground to dissolve the uranium right out of the rock, then pumping the liquid back to the surface. Once the ore is hauled out of the ground, the real work begins. It's taken to a special processing plant called a mill. The first step is to crush and grind the rock into a fine powder, almost like sand. This increases the surface area, making it easier to get the uranium out. The powdered ore is then mixed with chemicals in large tanks, usually an acid or an alkaline solution. This liquid leaches the uranium out of the rock, dissolving it into the solution while leaving most of the other waste rock behind. It's a bit like making a cup of tea, but on an industrial scale and with much stronger chemicals. After leaching, you're left with a uranium-rich liquid. The next step is to get the uranium back out through chemical precipitation and purification. The end result is a coarse powder called uranium oxide concentrate, better known as Yellowcake, only mildly radioactive, ready to ship for the next stage. The uranium atom. To really understand uranium, we need to zoom in, way in, to the atomic level. An atom is like a tiny solar system. At the center, you have the nucleus, which is made of particles called protons and neutrons. Whizzing around the nucleus are even tinier particles called electrons. What makes an element what it is the number of protons in its nucleus. Every single uranium atom in the universe has exactly 92 protons. If it had 91, it would be protactinium, and if it had 93, it would be neptunium. That number, 92, is uranium's atomic number, its fundamental identity card, a family of isotopes. While the number of protons is fixed, the number of neutrons can vary. Atoms of the same element with different numbers of neutrons are called isotopes. Think of them as siblings in the same family. They're all uranium, but they have slightly different weights and properties. In nature, uranium is mostly made up of three isotopes. The big one, making up over 99.2% of all natural uranium, is uranium-238, or U-238. It has 92 protons and 146 neutrons. It's relatively stable, but it's not the one we're most interested in for making power. The special one, uranium-235. The real star of the show is uranium-235, or U-235. It makes up only about 0.7% of natural uranium. Section 6. The bright side. Power medicine discovery. The most well-known benefit of uranium is its role in generating electricity. Inside a nuclear power plant, the chain reaction of U-235 fission is carefully controlled. The tremendous heat released by the splitting atoms is used to boil water, creating high-pressure steam. This steam then spins a massive turbine, which is connected to a generator that produces electricity. The great advantage of this is the sheer amount of power you can get from a tiny amount of fuel. A single uranium fuel pellet, about the size of a gummy bear, can produce as much energy as a ton of coal. And it does this without releasing greenhouse gases like carbon dioxide. Uranium's influence extends deep into the world of medicine. While uranium itself isn't used directly on patients, fission and decay create useful radioactive isotopes. These radioisotopes are invaluable diagnostic tools. A small, safe tracer dose collects in an organ. A special camera tracks the radiation to create detailed images, helping diagnose cancer or heart problems. Concentrated beams of radiation, often from isotopes like cobalt-60 produced in reactors, are used to target and destroy tumors. Beyond power and medicine, radioisotopes sterilize equipment, irradiate food, and act as precise industrial gauges. Section 7. The shadow side. Dangers and dilemmas. For all its benefits, uranium carries a heavy burden of risk. The primary danger comes from its radioactivity. The radiation it emits, alpha particles, beta particles, gamma rays, is a form of ionizing radiation. It can knock electrons out of atoms and molecules in living cells, including our DNA. High doses of radiation can cause immediate sickness or death. Lower chronic doses over time increase cancer risk. This is why uranium mining, processing, and handling must be done with extreme care and heavy shielding. When people think of nuclear dangers, they think of major accidents. Modern reactors have multiple redundant safety systems and are statistically very safe, but the potential consequences of a failure are severe. The 1986 Chernobyl disaster in Ukraine and the 2011 Fukushima Daiichi accident in Japan both resulted in catastrophic meltdowns. They released radioactive material, forced mass evacuations, contaminated land, and caused immense social and economic disruption. Spent fuel is intensely radioactive for thousands to hundreds of thousands of years. Most is stored in pools or robust casks, while nations struggle to site permanent deep geological repositories. Section 8. Separating myth from metal. Let's bust a few myths. The first big one: all uranium glows in the dark. You see it in cartoons, a green pulsing glow. The fact: uranium metal itself doesn't glow. Some uranium-bearing minerals are fluorescent. They absorb ultraviolet light and re-emit visible light, the eerie green glow. Pure uranium metal in the dark looks dull, silvery gray. The glow is the mineral's property, not the elements. Misconception: all uranium is equally dangerous and ready to explode. That's not true. Natural uranium is over 99% U-238. It can't sustain a chain reaction alone. It's only mildly radioactive, though still handled with care. The potent isotope is U-235, less than 1% of what's mined. Enrichment is a massive industrial effort to concentrate it for reactors or bombs. Nuclear accidents are dramatic but rare. On deaths per terawatt-hour, nuclear ranks among the safest. Modern reactors add passive safety like gravity-driven control rods and natural circulation. While weapons exist, most uranium today is for peaceful purposes: reliable carbon-free power, medical imaging and treatment, and dating ancient rocks. Section 9. A careful future with a powerful element. So we've traveled from stardust to power plants, from myths of glowing rocks to the hard science of the atom. The story of uranium is a story of profound duality, born in violent cosmos, yet able to quietly and cleanly light our cities. It holds the power to create, to heal, and to reveal the universe, and the power to destroy on an unimaginable scale. Our journey shows knowledge brings responsibility. Learn from accidents, engineer safer systems, manage waste with rigor, and uphold robust international agreements. Scientists pursue inherently safer designs, less waste, even running on old waste, paired with public trust through open conversations about real benefits and real risks. Uranium is a powerful tool, here to stay. If we proceed with caution, respect, and clear-eyed facts, it can help build a cleaner, healthier, more prosperous future. That is the clear challenge at the end of our timeline.